Good morning again. Scientists and engineers have long looked to the natural world for inspiration in their designs. As artificial intelligence systems have grown increasingly more sophisticated, when we compare to what's really possible and around us every day in the biological world, we're way behind in many important areas. Things that jump to mind immediately are power efficiency, learning speed, or robustness to uncertainty and adversaries. Now, how do we take the inspiration from what we know is possible from the biology all around us and apply that to the microsystems of tomorrow? Really excited to get into this topic today. Eric, Andreas, Ron, welcome, and thanks for participation. Let's start out with the first question, which is that as we look to these very significant gaps, what are the core differences, the key differences between artificial intelligence systems and biological systems that could start to explain these differences? Eric, let's start with you.
Yeah, well, I think one of the things that's really interesting is to look at the concept of modularity in a biological system versus in an engineered system. So in an engineered system, modularity comes from the idea that we need to have multiple disciplines talking to each other. We need to have parts that work together without the engineers having to necessarily spend their entire lives working on something together. They can have an interface that's well-defined and allows them to scale and build things that way. Biology has no such constraints, so biology uses modularity to some extent to create diversity in how it uses molecules and proteins, for example. So it'll make a copy of a gene and then tune it into place over a few generations. But besides that, modularity is sort of messy in biology, and it's not really there to help people understand and manage complexity. And so it's very hard to understand biology in the first place. But because of that, you get this incredible economy of usage. So a protein or a molecule in a biological setting can be an energy carrier, it can be an information carrier, it can be structure. And it can do all these different things with the same basic building blocks using billions of years of evolution to tune it into place to do these things that are just sort of remarkable at that scale. So biology can interact with chemistry, electricity, with photons, with magnetism, with gravity, with touch, and strain and stress, and so many more things. So it's a really amazing set of building blocks that biology has tuned into place using just an incredible economy and billions of years of optimization to come up with these ideas. And I think there's a lot that we can learn by looking at how biology has used that economy to its advantage as we build more engineered systems that using more and more kinds of physics and more parts and more things to create diversity of function.
Eric, I definitely want to pull on those threads of modularity in a few minutes. But Andreas, what are your thoughts on these sort of key fundamental differences?
Yeah. So I would start by saying that the key difference on the performance side between the brains and machines is that our brains learn a world model. Like they're very good at basically being able to learn the structure of the world, and then they're very good at extrapolating to new kinds of data. Whereas if we look at machine learning, in generally speaking, they're very good at interpolating because they have trained on so much data, much more data than we ever get trained on. So this is the big fundamental differences between performance under IID conditions for the machines and under ours being able to extrapolate. So you can think of current machine learning algorithms, although maybe this is a little bit of an exaggeration, as sort of very, very fancy curve fitting algorithms. Now, if you look at the brain, one fundamental difference is that it's not, when we're born, and especially other animals, it's not born with a blank slate. It has a very strong inductive bias to learn from the existing data. So this is one big fundamental difference, is trying to understand what is the brain's inductive bias that enables it to learn so much more efficiently, and more importantly, learn the causal structure, the structure of the world, that then it can extrapolate to completely new situations. Now, modularity also at the circuit level is very important. Like we see that the brain is composed of dozens, maybe hundreds of different cell types. Neurons are the most complex cells in the body. And if we look at its connectivity, it obeys these power laws. It has a very sort of predefined structure. And also the learning algorithm itself is not, we don't think is gradient descent by backpropagation, but it has some local plasticity error. And if you take these things together somehow, and we don't understand it at the theoretical level from a neuroscience point of view, this introduces an inductive bias that when an animal is born or a human, it can learn very fast and generalize. For example, if you show a kid, examples of elephants, and then you show them a marble pink elephant, they will recognize it immediately. And the reason is because it has learned to disentangle these world variables. So I would say that if we can understand the brain's inductive bias at these different scales of analysis that also you guys discuss, I think that's going to be a fundamental thing in trying to then reverse engineer it to smarter AI.
Excellent. Yeah, a lot of threads I want to pull on there, but Ron, where do you think we should focus on as these key differences?
Yeah, so biology definitely does computation in a somewhat different way. I mean, we talked about the fact that everything in biology actually performs computation. So if you think about the DNA to the protein to the organelles in a cell to tissues, everything is continuously computing. Everything is also actuating. Everything is sensing. So every part in biological system performs multiple interactions, storage as well. And we mentioned the notion of modularity, the fact that there are certain aspects of modules in the system, but there's also a lot of messiness. There's parts that basically perform multiple tasks consistently, and they interact with modules in non-trivial ways. They also have to work with the certain constraints of the substrate, such as noise and stochasticity. So they've been adapted to actually function together as ensembles, rather than having a reliance on any individual element to perform things reliably. So these biological systems can fail if they weren't able to actually use heterogeneity as a way to gain robustness. Right? So if a single protein doesn't do its job, a single cell doesn't do its job, the tissue still is able to maintain overall functionality. So somehow the biological systems have been able to use emergence as a mechanism to actually obtain robustness in a way that we don't fully understand yet, and the notion of self-organization as well. Right? So the emergence of robust systems, rather than from a top-down perspective where you engineer each component to exactly fit within an overall structure, but rather the self-organization and cell-cell interactions that lead to the overall emergence of robust behavior. And so these are design principles that we don't really understand yet as engineers, as computer scientists, as computer engineers.
Excellent. Now, Ron, Eric, you and Eric both brought up this idea of modularity and how different that is in the biological world. I mean, we take it as a given that driving towards modular systems as engineers is sort of the cornerstone of what enables us to do design. Do we think that the concept of modularity, as it's applied in engineering today, is actually holding us back from realizing some of these advanced capabilities? Eric, we'll go back to you.
Yeah, I mean, I think that's definitely possible. At the same time, we do things in engineering that are about breaking modularity, or at least about making things less obviously modular. So think of it, for example, if I write a C program, I'm going to write it in a really modular way with lots of, one function, one purpose, one effect, right, or whatever. I'm going to declare my variables and do this thing. It's like a really modular way of doing it. But then if I want it to work really fast, I'm going to run GCC minus 03 on it and optimize it as much as I possibly can. And those optimization rules, right, are in a sense what biology has done sort of over billions of years to create lots of economy and lots of energy efficiency and all that stuff. So one of the things you can imagine doing is trying to understand how can we build something modular, but at the same time, how can we break that modularity as much as we possibly can in order to get better energy efficiency, faster interconnects, and all the other things that people have been talking about at this conference.
Let's pull on that thread even further, and Ron, let's talk about synthetic biology, which is really engineering systems to do compute from biological foundations rather than semiconductors. Can you talk about how that plays in?
Yeah, so when we started synthetic biology, I think the notion was, let's take principles that we understand in computing, computer science, and try to apply them to the biological world, and that allows us to demonstrate various devices, so basic building blocks, NOT gates, AND gates, and so on, and begin to put them together to slightly more complicated circuits. And I think in the initial phases of synthetic biology, that really allowed us to demonstrate engineering capabilities over the living world. But I think now we've actually reached a really interesting stage in synthetic biology where we are trying to understand the fundamental properties of biological systems and how those are different than the ones we're used to doing and the ones we're used to dealing with. And what does that imply with respect to the appropriate programming abstractions that work the best within the biological constraints? And so, for example, moving away from a digital abstraction and trying to understand how can we use digital, analog, neuromorphic hybrid systems that together work to create the desired behaviors. Understanding how we not just attenuate noise, but actually benefit from noise as well. How do we engineer systems where we don't have to rely on any individual component? How can we benefit from the noise aspects of the system? How can we talked about modularity? How can we benefit maybe or design messy modular systems that would be able to actually have individual pieces that can actually do multiple roles in different contexts? And so I think how do we also benefit from something called epigenetics? This notion that a cell can take the DNA that's inside the cell and decide, okay, now I'm going to activate these pieces of DNA and I'm going to shut down other pieces of DNA. So there's a whole nother control structure that's sitting on top of the DNA that's encoded inside the cell. And so the cells really provide a lot of really interesting biochemistry, which then can force us to think about new design principles, which I think we can then ultimately bring back into the world of electronics and the world of computing.
A core theme of the ERI Summit is heterogeneous integration. But all the discussions to this point have been talking about heterogeneous semiconductors. Yeah. What might it mean to have biological components integrated with traditional semiconductors? I'll leave it with you, Ron.
So we have to understand what the interfaces are. We have to understand the aspects of time scale separation, for example, the fact how electronics compute versus how they might be able to interface with hybrid systems. Imagine a situation where we have, maybe on edge computing, we have a situation where we have electronics that are also interfaced with brain organoids, right? The notion that we can actually take stem cells and then differentiate them to create mini brains that can actually function right next to the electronics. Understanding how those biological systems can perform tasks that are difficult in the electronics environment, how they can continuously reshape, how they can adapt, how can they modify the DNA, how can they modify neuronal connections, how they can use mechanisms to be able to sense the environment, but also modify the DNA in order to be able to accelerate what they can sense or modify what they can sense over time as they experience different environments as well.
That's a great point of connection to a thread Andrea started earlier, where we're looking at, Andreas, to what extent does the structure of the brain really enable some of these sort of outstanding learning speed, learning capabilities, robustness within the brain itself? And are there things that at the science level, at the neuroscience level, we need to learn more about in order to unlock those capabilities or even reverse engineer neural structures?
Yeah. So this is one of the remarkable things. When we look at the brain, we see an immense, complexity in terms of structure of many different scales, from the individual neuron to the circuits that form different networks in the cortex, the hippocampus, and so on. Now, we still do not understand how much of this structure, this complexity, is biological details of implementing a specific algorithm given constraints that biology has, that maybe microchips do not have, or whether they represent, or which ones represent this inductive bias that I was talking about, that then enables it to learn faster. So one way that I like to think about it, and it's related to the previous talk on NVIDIA, is that if you look at the CPU versus GPU, which has really revolutionized AI, it was a different architecture of the processor that enabled this parallelization and this idea that you could do matrix multiplications very fast to then analyze, be able to learn from all this data. So one way to think about it is that if we could understand the brain's structure and translate that to what this inductive bias is towards learning algorithms, and this is something that we still don't understand. I think this is an area that there should be more funding from neuroscience and engineering to understand the brain as a learning machine. Then I think this would inspire new principles that then you can engineer to build new technologies that will be able to do that.
Do you think the technology exists to do the experimentation
Yes.
necessary to build that understanding today?
Yeah. What is remarkable in the last 10 years, and a lot of it because of the Brain Initiative funding, that also DARPA has been part of it in some way, but mostly NIH and other agencies of the federal government, there's been a revolution in technologies to study the brain. Like when I was a graduate student, you could record from maybe dozens of neurons. Now there's technologies that enable you in an awake animal, a mammalian, to record, let's say, 1 million neurons simultaneously. There are ways to manipulate the genes, the neurons. So we've become very good at collecting huge amount of data, but we still have not achieved distilling this data into knowledge and understanding. So it's interesting because we're at a very important transition where we're very good at collecting data, but we do not know how to change this to principles. And I think that's going to be the next maybe 10 years. If there is hopefully a revolution in that, then I think that's going to have a huge impact in technology. But I think it's also important to emphasize that we need closer interactions between the engineers that are like building, manufacturing like chips like that will be used for artificial intelligence, and neuroscientists that are trying to understand the brain. Because in neuroscience, the way the funding works and the way the goals are set is not necessarily to reverse engineer your principles into a system that does, let's say, object recognition. So I think having more bridges between these two fields is going to be very important because we may be missing opportunities.
Absolutely.
Excellent. You brought up the idea of manufacturing, and I think that really offers another way to highlight key differences between biological and engineered systems. Eric, can you maybe highlight some of these, so the astounding differences in how these two systems work?
Yeah, I mean, absolutely. If you think about how we build semiconductor systems and chips at this point, right? We have billion-dollar factories. We have supply chains that span continents, the entire world. We have thousands of employees. We have machines that cost hundreds of millions of dollars to build and more hundreds of millions of dollars to maintain, to build chips. And then we try to make a chip we try to make 1 billion chips or something, and all of them are more or less exactly the same, as exactly the same as we can get them, and then we have to test them and make sure that they all work, and then the ones that don't work, we throw them out. Biology, in contrast, I can take a single yeast cell, because yeast is an organism we use in our lab, and I can put it in a test tube with some sugar water, and the dust in the air is nutrients, and the thing will, in about 4 hours, create 1 billion copies of itself. And not only is each one of those cells capable of information processing and sensing its world through all these different modalities, each one of those cells literally is the entire manufacturing plant. So it can make a copy of itself. And it does all of the things that our entire global system does in a single cell. It does breakdown of raw materials, purification, assembly of smaller parts into bigger parts, distributing parts among different parts of the cell in order to create other subsystems, repair, error correction, testing, right? So in a way, what we have done as humanity in building the semiconductor industry is we've made a cell, like a really big, crazy, kludged together copy of a cell that does like all these different things with TSMC as like the nucleus, right? Putting together like all the different parts with all these things coming into it, right? A cell can do almost all of that, and it can do it for essentially free, right? What we don't really understand is the complexity of the cell. Like I said, it's an incredibly complicated thing. So are neural networks, so are all the different cell types that we use. But we can basically print out a big piece of DNA, a piece of DNA that's like 12 kilobytes long, has 4 to the 12 kilobytes, right? 12 million possible different design spaces, and try to boot that up. And the other thing I'll add is if you look at the number of experiments that biology has done since we began this talk, right? It vastly, by orders of magnitude, has explored more designs than the entire semiconductor industry has in its entire existence, right? So it's looking at all these possibilities. Now, of course, you build a bunch of cells, and some of them work and some of them don't, and that's not necessarily ideal for the semiconductor industry. And you're trying all these experiments, but the variability, the ability to explore design space that comes from such an incredibly inexpensive way of manufacturing cells is something that I think ought to inspire us to figure out how to make these very complicated processes for making engineered systems simpler.
Yeah, excellent. I mean, that really does make you think about what is absolutely impossible in semiconductors is happening routinely all around us. So I want to pull on a related thread, and that's sort of these two timescales of learning associated with biological systems. We tend to focus on the short term, the sort of the lifelong learning in the lifetime of an animal, but of course there's this other timescale, the design space exploration that's really evolution. Ron, do you think that there are sort of elements of these two time scales of learning that can be folded back into microelectronics?
Yeah. By the way, I want to follow. Yeah, great
Please,
question.
go for it.
I want to just follow up on what Eric said. But when you begin to play around with the DNA and build DNA and realize that you can put that DNA into a cell and that allows you to program the cell, it is a really fun thing to do. So I encourage everybody here to at least think about thinking about it, trying it out or so. But it does, provide a new perspective on what you can do. And so in terms of building DNA, for example, right now we don't start with just building a single piece of DNA anymore. It used to be that, the design we had is we're going to come up with the best design possible. We're going to then figure out the one piece of DNA which encodes the perfect circuit, and we're going to put that in the cell and kind of cross our fingers and hope that it works. We no longer do that. And maybe there's some lessons for us here in this community as well. So we now oftentimes will not just come up with one design, 10 designs, possibly millions of different designs that we want to explore simultaneously. And the beauty in terms of a manufacturing perspective is that it's easy for us to generate millions of designs or even billions of designs and then try them out. And then with respect to getting these designs to work. So we can ask, do these designs work? But then we use other mechanisms that biology provides, such as directed evolution. So we can actually ask the biological system to evolve within the days or weeks when we're actually engineering the system. And we can ask the biology, come up with new solutions and test which ones of those actually work the best. And so the design, we get to explore a huge design space, by the biology being able to do that for us as well. And so the biological systems are essentially, learning, in a sense, on the fly, if we provide them the appropriate cues. Now we've also are beginning now to explore mechanisms by which we can also take control of that learning process in a more directed fashion, kind of benefiting from learning in AI. And so we are now exploring mechanisms whereby we ourselves are instructing changes in the DNA. Okay, and so not just randomly having them happen, but rather in a more kind of engineered fashion to see how these potential changes could then lead to, to better and better designs. And so I think there's a lot that potentially can be, brought back to microelectronics in that fashion.
Yeah. Excellent, excellent. Andreas, I want to pull back one thread, and that's looking at this idea that we don't know the purpose of structures today. I mean, in the brain, are there dangers that if we too closely follow the brain's example, that we might, say, miss out on opportunities to consume big data or other kinds of shut out paths that are available to us today?
Yeah, no, I think this is a very good question. And the analogy goes to like, in the early days of aviation, trying to replicate the bird flying versus building an airplane. And I think we have to be careful. I mean, our goal is not to copy the structure of the brain or biology, I think, but it's more like to engineer at the level of principles of organization. Like, for example, if we can understand the parallel connectivity principle of the brain, if you look at the brain and you look at it as a connectivity matrix, you get locally very dense connections and then structured sparse connections, more long range. If we can, and there are ideas out there, but if that was to be, let's say, explored more in chip manufacturing, where we see this in the brain and in biology, I think in general at those scales, then that would be one way to implement it. The other thing that I wanted to point out is, unlike the birds and flying, we are, in some ways, at least some part of AI is trying to replicate human intelligence. So we are trying to one of the goals at least is to build machines that we can interact with them and they will behave like us. But you're right that, there's a lot of other advantage that, microchip manufacturing has. For example, the fact that it can consume so much more energy and train on so much more data, so maybe thinking of these sort of hybrid systems, that some of these engineering principles, or maybe thinking of different, not like one technology solves everything, but maybe different technologies are optimized for different things. But in general, I would say that we're interested in reverse engineering principles. But often these principles come from people like engineers trying to implement and think about this diversity and this structure. And then there is this sort of flow of information back and forth.
Excellent. Yeah, I'll say, fortunately, we're out of time, but I do want to give everyone an opportunity to really, what's the one key message that you'd want to give to this community of the key core inspiration we want to take from biology? Eric, very briefly.
Yeah, sure. So, biology provides an existence proof that complicated information processing, self-replicating, learning, intelligent systems can be built in a variety of different ways. So what I would encourage you to do, everybody, go onto Amazon and buy a book on biochemistry and read it from cover to cover over the next few weeks. And just marvel at the ways in which biology has solved a lot of the problems in a completely different modality as you. And like Andrea said, you don't have to copy it exactly. You can do it in silicon, but it's inspirational.
So Ron?
So I would come back to the notion of messy modularity in a way that allows the system to react and adapt to the environment and be able to modify itself.
Excellent. And Andreas?
Yeah, I would say think of when we went from the CPU to the GPU and how it has impacted AI, and now think about the problems that, let's say, intelligence or the brain is trying to solve, and can we draw inspiration from the connectivity, the diversity, and the representations that we study in the brain to then engineer, let's say, the next phase of the GPU, or something beyond that.
Perfect. Well, thank you so much. This has been a really stimulating conversation. If anyone in the audience would like to continue it, please come find us on the break. Thank you so much.
Great. Thank you. Thanks.